Hello friends. So till the previous video we have discussed this RC circuit with the input excitation of a type step where we applied the step of 0 to 5 volt. So and after that I applied some higher voltage step of 8 volt, 10 volt. Then we have analyzed the initial slope and exactly how the slope of the capacitor voltage is changing. Accordingly we have drawn this characteristics. So what we have seen for the step input, the capacitor voltage was coming some sort of this for the 5 volt step. Okay, so the final value was near to 5 volt. VCT is equal to V out T, the T. Okay, depending on the initial slopes, you have the different values. Let it is for step of 8 volt. This was for the 5 volt, and let it is for 0 to 3 volt step. Okay, depending on the step, the amount of the voltage we are applying at the input, we are having the different initial slopes, so the final values are also different. Okay, so in this particular question or in this particular video, I'll discuss different kind of excitation where what we are applying the same step signal, but instead of staying at 5 volt forever, we are taking it to the low value again at t equal to t naught, and after that is staying at 0 forever. Okay, so with this we will analyze the thing. Okay, so what is happening at t equal to 0 positive here? T equal to 0 positive, we will see the simply the capacitor should be short. So what should be the VC 0 positive, which is also V out 0 positive equal to 0 volt. Okay, and let consider your means this input which is changed from 0 to 5 volt is not coming down. Simple step we are considering initially it. Okay, so what it will be, let's say equal to infinite, what will happen? We have seen the two states always. So we see infinite is V out infinite, and I'm considering the cap is open at that particular because DC is already there. This 5 volt is already set for a long time. So I'll say it is nothing but a 5 volt. Okay. So again, it should be some sort of 0 to 5 volt at infinite. But what is happening? Let's say T naught is some instant, and we will define the value of T naught. Okay, let's call this is the T naught. Somewhere here, let's say this is my T naught, and up to this whatever value we have reached, after that our input excitation again coming back to this lower value of 0 volt. So what should be there, and what should be there exactly, we'll see that. Okay, so now the point is that first thing, what is the value of this with respect to our time constant? Value of T naught with respect to time constant, which is a RC. Okay, tau is my RC. So what is the tau in general? Tau is nothing but when your any charging curve, which is the 63% of its final value, let us charging curves reaches is same like what do you say? Again the means 63, or from the other side we will say 36% of this value. Okay, so this is the tau usually we define. So if I say that my T naught is much greater than RC, let's say my RC is whatever the time constant, the T naught is very much greater than. So in that sense, what we'll consider, let's say my input is coming from 0 to 5 volt at t equal to 0. This is called t equal to 0, and after that is staying at t equal to 0 for a long time. And let's say this t naught is somewhere here, which is is very greater than RC. Okay, so because as your RC is small, RC is much smaller than the time T naught. So what is the RC small means? This output will VC of T will reach 63.7% value sooner. Or I will say, what is the usually we say steady state value? If I call it steady state value, for any charging curve, it is also defined by this thing. Usually we define 4 tau to 5 tau. So it is maximum 4 RC, or I will say to 5 RC. So if your RC is much lesser than this T naught, then I can say 4 RC is also very much less than the tau naught, or sorry, T naught, or I will say 5 RC is also much lesser than your T naught. So overall, what we can see, your T naught is very large. So whatever the phenomenon happening here, we are reaching from 0 to 5 volt, and this T naught, this particular case I mentioned here. But according to what our consideration is, T naught is very greater than RC. I will say somewhere here, or very long time, after very long time, my T naught is coming. Okay. So okay. So what will be happening here? What capacitor will see that it has 5 volt input excitation applied at t equal to 0, and this is applied for a long time. So capacitor will see what up to some here this time the capacitor will reach the 5 volt. Okay, and it will hit the 5 volt somewhere here only, the steady state value. So this is nearly the 4 tau, I should say, or to 5 tau. So somewhere here this capacitor is fully charged, so it is seeing nothing, no problem is there. And after that, what we will see, your input excitation is coming down to 0. Okay. So after, if I say what will happen at t equal to t naught positive. So let draw the circuit again. At that time, I have seen that my input is not there, and it is again came back to 0. And what is the capacitor voltage value at that time? Capacitor voltage reached to 5 volt now. Which is nothing but also my output voltage, which we have seen from this curve itself. This is the 5 volt here somewhere. It already reached 5 volt here only. So what to speak of the T naught? This is a 5 volt only. Okay. So now what will happen? Previously, when the capacitor was charging, the current was flowing in this direction. Now I am seeing that there is no excitation on input side. So what should be there? This the equivalent circuit is like that. Now, because capacitor is already charged and input side is nothing there, this is a ground. So I would say R. And what it will happen there, because my V out is 5 volt, at which instant? Let this circuit is at T equal to T naught plus. Okay, so this is my capacitor. Previously, the current was charging the cap. Now the cap has the voltage, but there is a no excitation, so cap will start discharging. Okay, so this is the direction of current IC. We'll draw this IC also, but before that, so this is the direction, and after that I am saying that input is not applied, so this is going to stay at 0 forever. Okay, so it is 0 at forever. So what will happen then? Okay, so what I'm saying, what is the I t0 positive? This is the direction that I am giving IC. In this direction only I want to see. So what is this? This node of capacitor has the voltage 5 volt. So resistor also 5 volt. So what is the IR actually? It is also the IR if I am giving this direction. So what is this? This is IR. It is nothing but 5 by R. Okay. So in that direction, okay. So this is the particular direction of current I am mentioning here. But actually, if I see what was the capacitor current, initially we have considered this direction. So in that respect, it should be negative. So what I mean to say, I mean to say the actual direction of capacitor current we consider this. So with respect to that, it should be the negative value. If I say IC0 positive, it is nothing but minus IR minus 5 by R. That is the thing that I want to make here. Okay. So yeah, yeah, 5 by R. So what is the means slope of this voltage of capacitor voltage? Okay, so what is the slope? Slope at t equal to 0 positive for capacitor voltage will be what? ICT0 positive by C, simply that we have already seen. It is nothing but minus 5 by RC. So this is the initial slope for the capacitor voltage. And after that, let consider some time instant of T naught plus some delta T. Okay. So the time instant here, T naught plus delta T. Okay, so now its voltage reduced because capacitor is discharging. Let for some time instant, this is the slope and this is the current. So this is the current flowing through the capacitor at some particular instant. Let's say that instant is nothing but a constant current of minus 5 by R is flowing across the capacitor. So capacitor will discharge. What is the equation of capacitor current? Sorry, capacitor voltage for that particular instant is 5 by RC times T. Okay, so some linear decrement will be there with that particular slope initially. This is all happening at T equal to T naught. Okay, so what is there? So capacitor voltage reduced because T is now reached to some delta T plus T naught. So this voltage reduced. And let's say this voltage reduced to 4 volt after discharging. So what will be the current at that time? It will be nothing but again minus IR at this particular instant. This is nothing but minus 4 by R. So what will be the slope at that instant? Slope will be slope at T naught plus del T plus what? Minus 4 by RC. Okay. So again, if I consider some other time instant that I call, what will be the current at that particular time instant? Let it del T plus some del T dash. Okay. So again, I will say these del T and del T dash are very small. Okay. Or I will say T naught plus del T are nearly T naught only, means they are just above the T naught, and this T naught dash plus del T is somehow greater than del T. Okay, so all are the small quantities that I want to make here because they are just greater than the T naught. I want to see the instants after the T naught time. Okay, so let's say at that particular point of time, my this capacitor voltage reaching to 3.5 volt. It is discharged by 1.5 volt voltage. So what will be the current at that time? Minus 3.5 by R. So what will the slope at this instant? Let this be less. So slope at this particular instant T naught plus del T plus del T dash. Okay, so slope will be minus 3.5 by RC. So no need to have any confusion with these del T dash. Simply I want to say if this is my T naught and after that if I'm considering this time instant, after that if I'm considering this time instant, and after that if I'm considering this time instant, we are seeing that slope is slowly reducing. Whatever we have seen in the current plot of capacitor initially in the previous question or previous discussion, the same thing is happening here. Okay, slowly slope is reducing and at after infinite time or T naught plus some large time, T naught plus large time, which I also called at infinite because there is no excitation now forever. So this completely will discharge to 0 volt. So what will 0 by R is nothing but 0. So what will the slope at that time will be also 0. Okay. So what we can completely see here that at T naught instant it was previously 5 volt. Now it is discharging to slowly to 0 volt. Okay, so this is the T. And before that it was settled to means 5 volt. So this is the capacitor voltage at T greater than T naught. Okay, so what will be the complete plot? Now come to the complete plot. So we have seen that as I told you, this is much larger. So from 0 to 5 volt, and after that it is staying to 0 forever. Okay, so this is the time instant. So what was happening here? So as my capacitor RC is much smaller, so it is like a capsule initially discharged and reaching faster somewhere here and is settled to 5 volt. Okay, and after that it is coming down to 0 and it is settled to 0 volt. So simply this is happening here. It is happening for T naught is much greater than your RC. Okay, so this is my T naught instant. So it is happening like this. Yes. So if now I am reducing this T naught, okay. So if I am reducing this T naught, let's say just we want to look from this graph only, what will happen? let I want to reduce this T naught to some sort of this value, and after that forever I'm staying at 0, 0 and 5 volt. And here also there is a possibility that I'm reducing the T naught only to the instant. So it is somewhat here, it is reaching the 5 volt, and after that it is reducing, and after it is staying. So this is my T naught. Same, if I'm reducing and continuously we are reducing, means T naught is greater than RC, means, or I'll say T naught is greater than 5 RC also. So it is well settled. I'm not worried about that. So if I'm reducing T naught such that we are coming lesser than this 4 RC or 3 RC or 2 RC or near RC, it means what is happening? I'm not giving the complete time for the capacitor voltage to reach its final value of 5 volt. Okay, so it means what I'm saying, if I'm reducing this T naught much, okay, so if I'm reducing this T naught much, let's say here, and after that it is staying at 0, oh this is 0 volt, 5 volt. Okay, so what is happening, actually this my T naught is coming somewhere here, so I am not giving time to reduce it completely to the, sorry, to reach the capacitor voltage complete to its value of 5 volt. If I'm not giving this time, let's say this is only reaching to some sort of 3.5 volt let. Okay, so I'm not giving the time to reach to its final value of 5 volt. So what this is a case, I'm considering that it is somewhere around less than RC or nearly RC, or I will say 2 RC. So it is some lesser time instant than that particular value. So what will happen after that? We have seen that my input excitation is 0. So whatever reached at 3.5 volt, accordingly there will be the initial slope of discharging, and it will discharge to a lot of 0 volt. Okay, so this thing we'll see here. Yeah, so from this graphical representation you can understand what I mean to say. Now I again draw the plot and we'll see this thing. Okay, so if I draw this plot again, sorry, draw the circuit again, C, V out, and this is the instant of time I'm applying here, 0, 5 volt, and this is the T naught we are talking about. Okay, yeah, so what we have seen, the after T naught, if I'm considering that T naught is of order of RC or is less than the RC, T naught is less than RC, or the case when T naught is much less than the RC. So what is happening? The capacitor is only charging, but it is charging with a few volts only, not exactly to the 5 volt. I will say it is reaching to, let's say, 1 volt, 2 volt, or whatever 3.5 volt I have mentioned here. So it is reaching to that value only. So what will happen after that? Okay. So the charging phenomenon will be same whatever it was. So let's say it is reaching to, okay. So let this is a 5 volt. This is a 5 volt. And it is only reaching to, now it is only reaching to, let's say, 1 volt or 3.5 I mentioned here, but I am taking here 1 volt, so no confusion. And this is the time instant T naught. And after that, what I am seeing here, my excitation is again coming to 0, and this is my R, and capacitor only reached to the value of, let's say, V out to 1 volt. So what should be the initial current? This is the circuit for T equal to T naught 0 positive. Okay, so what is the initial current at that particular instant that you will see here? What is the current? I cap, which is this direction. Actually I want to consider IC always in this direction, and so let this is my IR equal to minus IR at this instant of T naught 0 positive equal to what? Minus 1 by R. So what is the slope actually? For the voltage slope, VC or del VC by del T, or is the slope at this T naught plus instant will be what? Minus 1 by RC. Okay, so this is the slope. So what I'll say, this voltage is reduced. Now, okay, it is 1 volt, and what we have seen, the slope, initial slope here is lesser. In the previous case, what is was the initial slope here was minus 5 by RC. So here the initial slope is lesser. It means it will slowly discharge. Slope is less, so actually discharging time constant is same RC, but it is starting with a lesser value, so the initial slope is lesser. Okay. Anyway, the time constant is same, so it is not going to die slow or fast. But yeah, point here is initial slope is less. Okay, and after that, if I say after some time instant, this T naught plus some del T plus, let's say this voltage reduced to minus 5, or sorry 5 zero point 0.5 volt, so it is a minus zero point 0.5 by R. And what is the slope at that time? Del V C by del T. Slope at this instant will be minus 0.5 by RC. Okay, so it will be reducing from this value. Okay, from this value to 0 value, it will reach somewhere, and after that it will stay at 0. Okay, yeah, it will reach, and after that it will stay at the 0. So this is actually happening. So this thing we have seen. Now what will happen? Okay, now other case, what will happen? Pulse magnitude is increased. What I mean to say? For the same circuit, at this from 0 to 8 volt it is reaching, and after it is coming the same, everything is same, but this pulse amplitude we have increased. Okay, so this thing I initially started with a discussion. Then if I'm increasing the step size from 0 to 5 volt, and after that 0 to 8 volt, 0 to 10 volt, we increase like that only. So what we have seen, the initial current, okay, what we have seen, the initial current of charging for this capacitor, let this is called IC. So what was this? This initial current was what? Initially it was, when it is charging, only I am considering around this t equal to 0 point. Okay, so what it was there, it was initially was 8, and this voltage is 0 because capacitor is shorted, so 8 by R. What is initial slope? So here I will say initial slope of capacitor voltage is nothing but d by dt of Vc. 0 positive is nothing but 8 by Rc. So whatever was the slope in the case of 5 volt, the slope is now higher in that case. Okay, so what will happen here? Let's say my input is here, 0 to 8 volt. Here I want to see the VCT output. Let's say it is to 8 volt. Input is to 8 volt. After that it is coming to 0, and this T naught is much greater than RC. Again I am considering. Okay, so initial slope of the output is more. But anyway, we have to see one thing. We have to see one thing. Whether initial slope is more, but it has to reach some larger value. Previously it has to reach to 5 volt only. Previously its final target was to reach 5 volt only, but according to the 5 volt the slope was less. Okay, according to 5 volt the slope was less, so it took the same time, because anyway the time constant, which is tau RC, is same either in both the cases. Whatever the input excitation is there, we have the same circuit, so time constant is still RC, and the settling time, now what I call T settling, is again nothing but 4 tau to 5 tau, whatever we consider is a time. So it is not going to be same. So this is the thing I want to clear here. So when it was a 5 volt, the slope was less. When it was 3 volt final value, slope was less. So accordingly, initial slope was less, but overall where to reach, it is decided by the RC. Okay, this is the time constant is deciding factor of time constant is deciding factor for the final value, or it is called the settling time. Okay. So it has to travel a lot because it has to reach the 8 volt, and after the 8 volt again it is settled to this. So the same mechanism will repeat after that. I will not discuss this thing again. My point was here only that if it has to reach the 8 volt, some higher value, its slope is more. Okay, so nearly what I say, this time if I call this T settling, let's say it is a 4 tau, it is going to be same for all the cases. Okay, after that it will discharge, whatever it will happen, no problem. Okay, so this thing I want to make, let if I apply a pulse of let's say 10 volt, then what will happen? Initial slope will be more, but accordingly the final value will be settled. Okay, so here is your the tau, the TS is going to be same for all the cases, so final value is your 10 volt. Okay, so this was the case for this. Again for the 5 volt also it was something like that. This was 5 volt final value, but TS was same for all. Okay, and this will come down from here, it will come down for him here. Okay, so what we can see, this settling time is same for all. As we can see, initial slopes are different. So initial slopes are dependent on what do you call, the magnitude of excitation, magnitude of the input excitation. But time taken in final settling is independent of input excitation, as it is a nothing but tau is a function of circuit elements. It is not a function of input excitation. Time is not a function of input. Time means time constant is not a function of input. What I will say here, it is a R Thevenin C. Here R Thevenin is R only, so RC. Okay, so this is the thing that I want to clear here. So I think we have seen with the pulse input what is happening here. If my tau is very much greater than and very much less than the RC, and if it is exactly RC, then what will happen? You can see this also. If it is exactly equal to RC, then what will be the value? Value of capacitor voltage will reach to 67%. Sorry, 63.7% of final value of, let's say final value is 5 volt. It will reach to that value, and after that it will come down and discharge it. Okay, so this is the thing. Whatever with respect to RC, we can see up to what value my capacitor is charging and what is happening. So the other thing, now I want to see the capacitor current. Okay, yeah, now we want to see the capacitor current. So actually when we are drawing the capacitor current, we have to intact whatever the direction we have considered initially. This is C, V out, and this is my IC. Here I am applying the input 0, 5 volt equal to 0, t equal to t naught. Okay, so let's say the case t naught is much greater than RC, and what will happen? My current will start and it will reach to 0. What I mean to say, IC 0 positive is what? Simple 5 by RC. I am talking about the time instant around the 0 positive. Okay, so it will be 5 by RC, and after that it is reducing slowly. Let's say time instant some 0 positive plus some del t, it is reduced to 4 by R, and slowly we have seen this, it will reach to 0 ampere because your T naught is much greater than the RC. So in this duration, when your this is changing to this, okay, after that is 0, this is my T naught, which is much greater than the RC. This is due to 5 volt. So what is happening with the current? I'll say draw this on this only. So initially this, let's say the current was, I want to make a different label for the current. So let's say it was initially 5 by R, and after that it will reduce to, okay, yeah, after that it will reduce to some 0, and it will stay at the 0. Yeah, it will stay at 0 till this, when your voltage is 5 volt, till the time your voltage is 5 volt. Because here we have seen the what was the voltage? Voltage was 5 volt. The voltage reached 5 volt very soon. If I say here, my voltage reached somewhere here the 5 volt, okay, and it was staying the 5 volt. See, they are overlapping. Just it is a point of drawing. It is not going up, but it is, they are overlapping. Yeah. So after this, what will happen? Let I should remove this T naught. Okay. So here I am marking the T naught. So what will happen with the current after that? After this point, this is the T naught. Let me see what was my circuit for T is equal to T naught positive. My excitation was not there. So this was my R, and this is my capacitor, who is well settled to 5 volt, and after that it will start reducing. I'll consider the same direction for the capacitor current. Capacitor direction I am not going to change, but the current will flow in this direction. So whatever the current of capacitor at this particular instant, in nothing but reverse minus 5 by R. And after that we are seeing that slowly it is reducing from minus 4 by R to some sort of to what 0 volt, sorry 0 ampere. Okay, because finally it is discharged. So what will happen, so suddenly at this instant your current will go negative, and let call it okay, this is my axis. Let it draw properly. Hmm, okay, yeah. So okay, so this is my y axis. Here somewhere here it is minus 5 by r, and after that what is happening here, we have seen this thing from the equation and also from the intuition. After the minus 4 by r or 2 3 minus 3.5 by r to 0. Okay, so it will reducing means it is some sort of charge equation and it will reach to 0. So exactly what is happening, the current is following such sort of equation. Let this is my IC, this is the T. So it was previously coming down from this value to this value and was staying for a long time. After this, we're going reverse, and now we're going to charging and this current. So this is my capacitor current. Here it was the 5 by R, and here this value is your minus 5 by R. So this thing is happening for T not very greater than RC. When T naught is much lesser than the RC, what will happen? This is nothing but a point of your homework. You have to draw this IC plot for this particular case. Okay, and analyze it properly. So this thing we have seen for this particular input excitation. In coming video, we will take some different excitation and we will do the more analysis for this particular RC circuit. So this is enough for this video. Thank you.